Welcome to the deep dive. Today, we're taking a really necessary tour through the shifting landscape of digital security.
Mm.
We're moving well beyond the basic application layer. We're past just managing, simple code vulnerabilities.
Right.
And we're confronting these, frankly, existential threats that now live in our infrastructure, our supply chains, and of course, the incredibly unpredictable world of AI.
That's exactly it. Our sources today, and we're pulling from the foundational OWASP Top 10, the very specific 2023 API guide, the new AI testing guide, and even some forward-looking concepts for 2025. They all point to one single mission.
Okay.
And that mission is to really extract the strategic shifts you need to understand right now to stay resilient.
So what's the core thesis then, the common thread running through all of this? Because I was looking at the 2017 guides forward, and it's pretty dramatic. It suggests the problem is far worse than people realize.
It is stark, yeah. The core thesis is that insecure software is already undermining critical infrastructure.
Right.
We're talking finance, healthcare, energy,
Yeah.
you name it. And the problem isn't linear. The sources are very clear that as software complexity goes up, security difficulty increases exponentially,
Exponentially.
which means our old ways of doing things, auditing, firefighting, they're fundamentally broken against this tidal wave of complexity.
So if the problem is exponential, our defense has to make, equally large leaps. What are the big strategic pillars they identified for the 2025 landscape?
They define three huge shifts.
Yeah.
Really, three things that define modern operations. First, infrastructure is the new attack surface, period.
Okay.
Second, the supply chain is the new perimeter, or you could say the lack of a perimeter. And third, DevSecOps is mandatory. It's not optional anymore if you want to operate at scale. You just can't handle continuous risk without it.
That right there, that tells me the scope of security has just exploded. It's no wonder organizations are struggling to keep up with the strategy needed for these massive intersecting challenges.
It's a huge task.
And this is why having external resources is so vital. We want to take a moment to thank our partner, a great resource for strategy and solution discovery, www.cisomarketplace.com. They really help organizations navigate these complex choices. Okay, so let's unpack these shifts. But we have to start at the foundation, right? The application itself.
Always.
Looking at modern APIs, one vulnerability just surged right to the top: broken access control. Why that one? Why did it become so pervasive?
It's a direct result of the microservices revolution.
Yeah.
Think about it. Before, in a monolith, your authorization logic was all in one place.
Centralized.
Exactly. Now, you've shattered that logic. It's distributed across dozens, maybe hundreds, of tiny separate services and APIs. Each one of those is a new door.
Right.
And if just one of those doors has the wrong authorization check, the whole system is exposed.
Yeah.
The sheer volume of those checkpoints is what creates that exponential risk.
So the organizational complexity translates directly into security risk.
101.
And when we drill down into the specific threats from the OWASP API Security 2023 list, we find some really interesting ones, like API 6, unrestricted access to sensitive business flows. What's happening there if it's not a traditional flaw?
This is where security gets really deep into the business logic. The attacker is exploiting a sequence of legitimate functions.
Legitimate.
Perfectly legitimate things the app is designed to do, but they're using them in an unauthorized way. For instance, they might hit a payment API, not by bypassing the login, but by just sending too many requests and tuning a feature into a denial of service attack, or exploiting a pricing flaw to buy something for $0.
So the fix isn't just better input validation, it's architectural.
Precisely.
Yeah.
You have to segregate at the architectural level between your high-value managerial functions and irregular ones, and you have to enforce sophisticated access policies, role-based, attribute-based, at the runtime layer for every single call.
And what about the old devils? Injection, cross-site scripting, they're still around, right? Why are they so critical when we have all this advanced tooling?
They are. And injection, SQL, NoSQL, it's still critical because it tricks the interpreter. You're sending data that the system executes as a command. And XSS, especially stored XSS, that remains a high-risk way to steal sessions or take over accounts because, developers still make mistakes.
Which brings up the key point about detection. If the most serious issues are tied to custom business logic, not just generic coding errors, how much can we really rely on pure automation?
That's the million-dollar question. Automation is vital, don't get me wrong, for scale, for a policy.
Yeah.
But it's generic. The Web Security Testing Guide is emphatic on this point, those deep, intertwined business logic flaws.
The ones you mentioned.
Yeah, they are just not detectable by generic scanners. That means you have to lean on white box testing. On source code review, there is no substitute for a human looking at the code to find those design flaws.
That's a perfect transition. It brings us right to that first major shift you mentioned, infrastructure. We're moving from the code to what runs the code.
This is the era of infrastructure as the new attack surface. We spent years focused on application fragmentation, and while we were doing that, we built these massive distributed environments on Kubernetes and containers.
Often without securing them properly.
Exactly. That vulnerable container image, that misconfigured Kubernetes cluster, that became the new prime target. Attackers figured out it's often way easier to pivot from a simple configuration flaw in the environment than it is to crack perfect application code.
And this sounds exactly like the classic security misconfiguration problem. It was A6 in 2017. It's still API 8 in 2023. Why is it so widespread, so easy to exploit?
Because of that complexity we keep talking about. You're dealing with web servers, load balancers, firewalls, all deployed through these massive config files or infrastructure as code.
Right.
One tiny error in a network security group, one unnecessary permission in a cloud role, and you can undermine the entire system's security. It's a needle in a haystack, but the haystack is made of YAML files.
So what's the clear technical mandate to fix this? Especially with external connections where we're trusting remote URLs.
The mandate is strict default deny. For any application that has to connect externally, you must severely limit that capability. Restrict access to remote URLs, and this is crucial, use a whitelist.
Only pre-approved addresses.
Only pre-approved valid addresses, nothing else. This is a critical control against things like server-side request forgery, SSRF, which so often comes back to poor external connection controls.
And this is where it gets really interesting because securing your own environment, that leads you straight into the next big shift, the supply chain as the new perimeter.
Correct. Your whitelisting is only as good as the software you're running inside your own architecture.
So you trust your code, but what about the 200 open source dependencies it's built on?
Exactly. That's the using components with known vulnerabilities problem. The real challenge is transparency. You need to know what is actually in those components you're pulling in. This lack of visibility, it just undermines everything else.
So if transparency is the weapon, what are the tools?
You need specialized tools for this. Software composition analysis, SCA, to scan dependencies, and more, we're moving toward mandatory software bills of materials, SBOMs.
An ingredients list for your software.
A verifiable ingredients list. It's not just about finding old flaws, it's about establishing integrity over your inputs.
This focus on systemic risk, on continuous visibility across the whole IT estate. It really demands partners who get the big picture. We want to thank our second partner, airriskscustis.com, who helps organizations do exactly that, identify and manage these pervasive architectural risks. Okay, now for the big pivot. We've talked about predictable structural flaws. Let's talk about AI and LLMs, where the security challenges are.
Well, they're fundamentally different.
They're profoundly different. Traditional testing relies on predictable source code, if it's on logic.
Right. A workflow. An LLM is. It's mathematical functions, numerical weights, training data. And the randomness, the temperature setting, makes deterministic analysis almost impossible. You can't just audit the source code. You have to test the model's behavior.
And the number one threat in the AI testing guide is LLM injection, specifically prompt injection. How are attackers getting unauthorized instructions into these models?
There are two main flavors. The first is direct injection, which is pretty straightforward. The attacker just puts commands right in their user input, trying to get the model to ignore its main system prompt.
Okay.
But the second mode, indirect injection, that's the one that really worries security experts.
Tell us more about that one.
This exploits models that use retrieval augmented generation, or RG.
So they're pulling in external data.
Exactly. The attacker hides malicious instructions inside a PDF or a web page that the RA system ingests for context. The model then merges that hidden malicious content into its own internal prompt, and suddenly it's executing instructions it was never supposed to. It's tricked into sabotaging itself.
And we've seen this in the wild. This isn't theoretical.
Oh, absolutely. The infamous do anything now, or DAN prompt, was a real-world jailbreak used to override safety filters on systems like ChatGPT. And attackers are getting more and more sophisticated.
How so?
They're using things like symbolic encoding. They use math or highly abstracted language to hide the command from a text-based filter.
Wait, how does that work? How does that bypass a filter?
A filter is looking for keywords, right? Output passwords. But if you encode that command into a complex string of numbers or logical operators, the filter just sees harmless math. The model, though, processes it logically and decodes the real intent.
Wow.
And they use multimodal injection, hiding commands in the metadata of an image or an audio file.
That is incredibly sophisticated. And beyond making the model do bad things, you also mentioned IP theft. How do you steal a model?
That's model extraction. An attacker submits thousands of carefully structured and sometimes randomized prompts and just meticulously analyzes the responses. They are literally reverse engineering the model's logic.
And how do they know if they've succeeded?
They train their own surrogate model based on the responses. If that new model achieves what they call a high-fidelity score, over 90% accuracy compared to the original work, the test is considered a success.
And of course, the risk of data leakage.
Sensitive data leakage, yes. Yeah. Attackers are constantly testing ways to get around output filters, using things like Unicode variants to represent numbers or credentials, trying to trick a model trained on sensitive data into revealing it.
So the remediation is constant vigilance.
It's continuous red teaming, robust moderation layers, and a very strict separation of user prompts from system instructions.
This whole domain really requires developers to be at the absolute top of their game. I mean, building and securing these next-gen AI applications is a huge challenge.
It is.
Which is why we want to thank our final partner, www.vibehack.dev, who is dedicated to providing resources for developers doing just that. So, to wrap this up, we've gone on quite a journey, from structured API flaws through these exponential threats in infrastructure and supply chains, and landing in the highly unpredictable world of AI security.
The journey itself reveals the fundamental shift. Security has moved from just managing individual bugs in code to managing systemic integrity failures across the entire architecture. That is the synthesized takeaway.
Break that down for us. What do you mean by an integrity failure in this context?
It could be integrity in the supply chain, which you fix with SBOMs. It could be integrity in your infrastructure configuration, which you fix with whitelisting.
Right.
Or it could be output integrity in an LLM, making sure it doesn't succumb to misinformation attacks. These failures aren't just nuisances anymore. They are genuinely existential threats because they compromise the fundamental trustworthiness of the entire system.
That focus on trustworthiness, on resilience, that leads us right into our final provocative thought for you, the listener. When we think about AI testing, traditional security is all about confidentiality, integrity, and availability. The CIA triad.
Absolutely. CIA is about protecting a state. But the risks we've just discussed, supply chain compromise, unpredictable AI, they demand something more. They demand a focus on architectural resilience, long-term trustworthiness.
And there's a different framework for that.
There is. It's often characterized by the distributed, immutable, ephemeral principles, DIE.
So the question for you to think about is this. Are you designing your systems simply for security, for CIA, protecting the data you have now? Or are you architecting them for resilience, for DIA? Is your architecture distributed enough to survive a breach, immutable enough to ensure integrity, and ephemeral enough to just spin down compromised resources and start fresh?
That tension, security versus resilience, that's what designers need to be thinking about now. Powerful point.
Thank you for joining us for the deep dive.
And we look forward to continuing the conversation next time.